Okay, here we are in Math 1101. This is the lecture scheduled for April 5 and 6, although it's available more than a week earlier than that in case you just feel like getting it under your belt before you go on your break. Uh, Certainly have a nice break, whether you're already done with it or about ready to have it. That's certainly great. So let's take, first of all, an overview look at Chapter 6.4 because the book, well, the slides just didn't do it justice. And then I also plan to look at most of the chapter quiz. There are a couple I'm going to not do too much on. The standard deviation problem was far too difficult, plus I did that in class already to the level that I'd like to take it, which is a lot lower level than what they had in mind. Well, statistical inference is the main part of this, but they use clinical trials and effective drugs, and that's certainly been in the news with COVID-19, obviously. And so they want to try to find the efficacy of a particular drug or lack of efficacy of a particular drug, its effectiveness. And so they have several things that can be done. I guess I can run quickly through them. Some of the homework assignments touch on these things. And by the way, the WebAssign homework doesn't have a lot of numbers in them, except 6.3, 6.4. So I'm going to lean towards the numbers in the test, as I said in class. But even so, there's still more important stuff that, or some important stuff doesn't have too many numbers in it. And yes, some of the problems on the test may involve some of this stuff. So here are key ingredients when planning a clinical trial, which has certainly been in the news, even though it's been an emergency kind of rushed basis. Researchers first decide how much of a difference between groups is medically important. They decide how many subjects should be enrolled in the trial. Generally, the more the better. Should be enough participants for them to have confidence in the results. And when you get into the thousands, that's usually pretty solid. Okay, assuming that, well, next part of the group is given the drug or treatment, and the other is given a placebo. And the placebo, which is like a sugar pill that doesn't really do anything, except maybe it could be a kind of a mind trick, and sometimes people psychologically are incentivized to become well in certain relatively mild situations. I guess that's been known to happen. And it's called the control group, by the way, the one that's not getting the drug. And then they look and see what the subjects have, whether there's a significant difference between their conditions after the trial. Keyword is significant. That's where statistics comes in. And we'll talk about the p-value again that's shown in the slideshow. So I'm not here to duplicate it. I'm here to kind of add to it. And they talk about double-blind experiments, and there's no bias at all. The subjects don't know who's getting the drug, and even the researchers don't know. So there's no like, oh, here, you're my sister, I can give you the drug, and yeah, don't tell anybody I told you, that kind of stuff. So that would be completely ruled out. And I'd say a lot of the time that wouldn't matter, but just to be absolutely sure, that's a way of calling it double blind. We have a few things that we looked at already. I'll give you the try it yourself, for example. Which ones of these seem to be statistically significant, or in other words, rare? You flip a coin twice, get heads both times. Well, that's no big deal. That's actually one chance out of four. 1/2 times 1/2. That's a 25% chance. That's not rare at all. Or maybe you're driving and you pass three 1951 Studebaker cars in a row. Now, I wouldn't know what that looked like, but I'd certainly recognize an older car, one from, say, the 50s. And if you saw three in a row, you might think you're in some sort of fair or auto show or something like that. That's about the only time you'd ever see that, unless you're just watching a movie or something based in the 50s. So anyway, they go through a few other things that you can read. I can't go through every single thing here, but we did talk about the p-value, and it talks about the probability that an outcome of a clinical trial would occur by chance alone if the treatment had no effect. And if that number is small, that's considered quite rare, and that means the event is unlikely due to chance, and then it's called statistically significant when that number gets below 5%. That's the usual criteria. There are other criteria, but we'll just use 5%. So to go to the Vioxx thing, and I think we did talk about that one a little bit. And here's another one that's a little complicated. Let me see if I can summarize it so it's understandable. And let me see if I can increase the size just a little bit, maybe. Suppose we test a drug that we believe might prevent colds. There's no control group in this case, but suppose we know on average half, 50% of people will get colds this winter. This is back when only people were worried about were colds. Back in the good old days, I guess. Suppose we treat 100 patients with this drug, and instead of 50, we get 55 did not get a cold. Okay, so this is the idea of preventing colds. So that's the success. The thing we're talking about is preventing. So 55, kind of close to 50. Would we have concluded the drug is effective? Or would it be just by chance? My guess is it's just by chance. It doesn't look like it's that much different. So here's the idea. Without treatment, half of them would get colds. From this fact, it follows the probability of 55 or more, given that, works out to be, by computations, that's not too hard to do, about 18%. 18%. That would be the p-value 0.184 for this experiment. It says that in about 18% of observations of 100 untreated subjects, we expect that 55 or even more will not get a cold just by themselves. So this doesn't look very effective. It's not very unlikely. It's slightly unlikely, I guess, but it's nowhere near in the neighborhood of 5%. It's almost 20% of the time, even without treatment. So that's no big deal. 55 is pretty close to 50, no surprise. But what if we get 65 taking the drug did not get a cold? Okay, well, that's becoming a little tougher to do. That p-value, without showing the computation, would be only 0.002, 0.2%. That's the probability that 65 all the way through 100 patients would not get a cold if the drug had no effect. But that's not likely at all. That's not likely at all. Just by itself, if the drug was just a placebo and had no real effect, then you get 2 times out of 1,000 times where this might happen. But that is considered rare. We're not betting on that, in other words. It's just like, in a way, it's like gambling. It's like, where do you put your money? And this is not over that line of 5%, not even close. This is considered rare or statistically significant. So if 65% of the patients taking the DES drug did not get a cold, it is reasonable to believe that something other than chance is at work. In other words, the drug appears to be working, although they may be careful not to exactly say that, but they may infer that it is very likely that the drug is doing its job, which is all people really want to hear anyway. There's no such thing as a 100% guarantee right away, but at least they would be pretty confident about it. So when the p-value is small, the outcome is due to something other than chance. But it doesn't say what that something is. So that's also important to be careful with that sort of thing. Correlation and causation. And here we talked about correlation, of course, whether it's positive or negative and that kind of thing. We talked about the balloon already. And here is another example that talks about regions of England, British regions. They carved it up into, 10 different regions. And I've never been there, but I've heard of some of these names. And here are the weekly expenditures in British pounds back before they were part of the European Union. I guess they're gone from that now. It talks about how much they spent per week on alcohol and on tobacco. And the first thing I notice is alcohol expenditures are more than the ones on tobacco, but they're more interested in a linear correlation between the two variables, spending on one and spending on the other. Does the increase in one tend to increase the other, or are they completely independent? That kind of thing. With me, I like an occasional beer, but I never smoke, so that's just me. But there are people in Britain perhaps have different habits. Maybe they're just really keen on both of them. I don't know for sure. Well, anyway, they plot the points here, and here are the points by themselves. So alcohol moves from left to right from about 4.5 up to almost 7. Tobacco, in terms of the cost, goes from about 2.5 all the way up to about 4.5, and they tend to be more or less associated with each other. They even came up with a regression line, which you are not responsible for. But we can actually use the regression line. We don't plan to really do that, but we want to take a glimpse of it. So as the regression line comes in from technology, and yes, there are formulas, but no, we're not going to get there. We could then use it by saying if somebody spends an average of 4 pounds per week on alcohol, that would put them way back here, 4 pounds. Then they would be, as you plug in the 4 to the x, because x would equal 4, they show the work right here. You take that number, 0.612, multiply by 4, then add in this constant, which is just to keep it from being rough around the edges. And you get to around 2.5, 2.6 or so, 2.56 pounds per week to be spent on tobacco. So back over here where alcohol is 4, you'd be at about 2.5 or so, right about there where I'm pointing. And indeed, that line is pointing right there at that one prediction that they're trying to make. The couple of small things I could make is that that's not exactly inside the region of what we found, because the smallest value for alcohol was like 4.5, and to back up too far out of the bounds of predictability can be an issue, but I don't think this is far enough away for it to be a problem. Plus, it made it to the textbook, so it must be okay. So anyway, that's the idea of the regression line, how it can be used to make predictions. Some predictions are quite good, some points are sitting practically on the line, and others are not. This one apparently spends a lot more on tobacco than was expected. So that's going to happen. This person spent a lot less on tobacco than expected as you move up and down the Y direction for tobacco. Using alcohol as going first, like X, and then Y following it as the dependent variable. You can kind of look at the vertical distance between the two, and some are rather large and some are not. But that's the line of best fit. We're not really going into the details. We already looked at this one about the having all your teeth pulled out. That's such a fun one. Another one would be comparing these animals, and some of them are very small, like a deer mouse, 3.5 inches. Cheetah, however, is very large, almost 4 feet long. And then the speed in terms of feet per second tends to go along with the size. You can just see it's increasing, just like these were. They even graph it. And yes, this is very much lined up. It turns out it's very linear. We are not getting our correlation coefficients here. Notice they are, I'm sure they're very strong. They just did not bother to tell us what they were, because I know that was part of our coverage. We'll get to that. Anyway, they have another regression line that technology gave us, and looks like all of them are close fits, except for maybe the one that's second largest, which would have been the red fox. That one's just a little bit off for whatever reason. But these are just randomly picked animals, so I'm surprised it's that close. So here's where they talked about the correlation coefficient and some examples that we already showed you on the slides. And yeah, positive correlation definitely is positive. This one's a perfect correlation. It's perfectly lined up, although it doesn't look perfect. Here's perfect negative one. We already looked at those. This one's close to 0, hardly any correlation. This one's negative 0.77. It's generally heading downwards, but not in a perfect straight line, though. A little harder to make a prediction. And we talked about, moderate, strong, and minimal or weak correlation on those, and talked about all of that. So causation, let's see, where are we on causation? That would be over on the other page. I have to kind of keep two sources going at the same time. And yeah, so this one is an interesting one. Being bored could be bad for your health, so that's an interesting one. The more bored you are, the more likely you are to die early. So don't be bored. Find something you like and do it, provided it doesn't harm you in some way. Anyway, this article suggests that there's a link, positive correlation between boredom and early death. So you don't want to be bored, apparently. But anyway, they go through and all this kind of stuff. And a few other things I'd like to say. When two quantities are correlated, there are 3 possibilities. One causes the other. That's the one that a lot of people think of. Or maybe both are caused by something else, a third variable that is not mentioned. But if you think about it, maybe it reveals itself. Or it's possible it might be just coincidence, just pure chance. I heard that they were trying to correlate boxing champions with fashions around the turn of the 19th century or 20th century. Yeah, that doesn't seem right. Like the height of boxers versus the height of dresses or length of dresses. Well, and they could find a correlation, but does it really mean anything? No. And of course, here's a good example. Suppose a mother notices from time to time her baby gets a runny nose and a cough. The cough seems to come first most of the time. She concludes that the cough causes the runny nose. Well, in fact, the most likely explanation is they're both caused by a third factor. Simply, the baby has a cold. What a surprise. That they occur together and they're correlated doesn't mean that one causes the other. It's just there's just this third overriding factor that kind of goes through it. And they talk about the tobacco and the alcohol, and here's a fairly high correlation coefficient of 0.78, and it confirms the positive correlation. And it's possible that one may cause the other, like when people drink a lot, maybe they break out the cigarettes and they haven't smoked in years because they're drunk. That's a possibility. Or it's possible that people have a tendency to use one, may also often have a tendency to use the other. Well, yeah, I know some people like that, although in California, we're only second to Utah in less smoking versus any other state in the country. So at least that's the last data I saw. I think Colorado's doing pretty well too. But anyway, whatever. Anything in moderation, I guess, is okay. But cigarettes are just definitely harmful. So I can't really say that about cigarettes. Placebo. So they talk about this kind of thing. And there was a couple of other topics I wanted to say. Showing the causation requires more evidence than showing correlation. But enough research has been done to convince the medical community that that smoking does cause lung cancer. So just very quickly through here, classic example of an argument about correlation versus causation is the connection between smoking and lung cancer, a debate for many years. Many studies have shown that smoking and lung cancer are strongly correlated positively. And it's indisputable that smokers have a much higher rate of lung cancer than non-smokers. But the tobacco industry has argued in the past that it doesn't mean that smoking causes lung cancer. They're not 100% sure, but then statistically, nothing is ever 100% sure. So you get to 99.99999% sure. That's probably close enough, but not for them. Not to pick on anybody in particular, but they have suggested it may be like the baby with a cough and runny nose. They may occur together. Maybe something else is doing it. They argue maybe there's a gene or some other unknown behavior that increases the propensity for both smoking and lung cancer. But anyway, that's one that's been clearly debunked, obviously, over the past several decades. So anyway, they talk about some of the answers to some of those try it yourselves that we looked at before. Of course, we have a good summary here of the chapter, which you definitely should look at, which we'll may cover again on our next lecture when we're back live on April 7 and 8. And here's the standard deviation formula, but the steps are just as important. So they go through here and get the deviations. Once you get the mean, get the subtraction of the mean, square the deviations, add those numbers, divide by n, and take the square root. So once you practice those steps, it should become natural to you. And I pledge to give you an example that will not really be very difficult. So like one I did earlier. And the bell curves, some are narrow bell curves and some are wider bell curves. There's a standard deviation of 100, there's a standard deviation of 50. And then, of course, the rules regarding 1, 2, and 3 standard deviations and polling and effective drugs and things like that. So let's take a look, if we will, at the chapter quiz. I don't have a lot of room to write on these. So as I get to the bottom of the page, maybe I can actually get to something that I can type in. So maybe that's the plan. I could squeeze the page down a little bit. So another soccer example. This one, these are all good problems. I'm not saying I'll put them all in there. I can't. But certainly this will represent highlights of many possible choices. The mean of this kind of thing would be relatively easy to do. Simply find the total number of goals. In other words, 0 times 7 is 0, 1 times 14 is 14, 2 times 11 is 22, etc., etc. You add up all those numbers, and you find there's a total of 130 goals. And the total number of games, 54. Apparently that's a season for them. And you divide that out, and you get 2.41 goals per game. This is total goals per game. So an average score would be like a 1-to-1 tie, or maybe 2-to-1, which is 3 goals, that kind of a thing. And that's the mean, 2.4. Median is a little harder to get, and I don't think I'm going to ask you this, but basically with 54 games, you'd have to go between the 27th and 23rd position. And so cumulatively, going from bottom to top, this is at the end of the 7th ordered game, and then add 14 more. Cumulatively speaking, that's the 21st game, and then you jump to the 32nd game. That means somewhere in this bundle of twos, and I don't want to write them all out, you would find the median of 2. Good enough. It's not very mathematical, I guess, but it works. And the mode is the easiest of all. Just simply grab the most popular one, or if there's a tie, grab them both. This time, 1 goal per game is the mode here, low-scoring situation. Now, the 5-number summary, first of all, you have to rank these numbers in order. So let me see if I can do that. And I'll do it in terms of thousands as I bring in the annotate. Oh, will it work? I guess not live, so I guess I can't get the annotate going. Okay, well, let's see. Maybe I should get this on the other scenario. So maybe if I can, hadn't planned on that. Okay, so maybe I can verbalize this somehow. Of course, this one's not too hard to do. The minimum is 17,000. Yeah, you look at that, that's the smallest number of all. And I could just read them verbally, but I find that suddenly I'm unable to type on the screen. I feel very awkward about that. What does this do? Does this give me, no, it just straightens it out. It doesn't give me a way to type. Okay, well, I'm embarrassed, but anyway, 17,000 is the smallest number. That is the minimum. And then the largest number is 32,700. So that's obviously the maximum. There are 10 values. The median will be between the 5th and 6th value. And so that would be between 25.6 thousand and 27,000. And that's the 5th value, the 27,000, the 6th value. Average those, you do get 26,300. And now with the quartiles, the idea would be to not include the median, but the median's not on the list anyway. We had to invent it. So to get the first quartile, you have to go and look at, say, the first 5 values and get the third one. So value number 3 happens to be 19,500, 19.5 thousand. And then go for the second half, and the middle value, the third value of that second half of the data would be 29,000. So that gives you all the numbers you need to get the box plot if necessary. And so the box plot would be not too hard to do. But I don't actually have this hooked up to use my pen. And I just now realized that, so I am a little bit embarrassed. So I'll try my best to walk you through this kind of thing. This does not give me an annotate situation. I found it somewhere, but I don't think I have it available now. So anyway, I'll just have to talk you through it, and hopefully you're following along with me. I decided not to do the mean and standard deviation. I had actually done this and found that the mean is pretty easy, 25,130. How does that compare with the median? Well, the median is higher, and that's not that hard to find when it comes to money type problems. So often the median is higher than the mean. This is not particularly bell-shaped most of the time when money is involved. Income or real estate, even prices of cars are not necessarily even, but then the median and the mean aren't that far off. They're only off by about 1,000, so I guess it's not that bad. But calculating the standard deviation is a mess. I should show you the notes I have. It's just awful. You subtract the deviation each time, and you get relatively nice numbers, but sometimes they're like $8,000, $7,000. But then the problem is you have to square those numbers, and that's where the fun begins. Somewhere around there, you get numbers like 57 million, 66 million, and you have to carry all the digits over. It's a nightmare. I'm amazed I actually covered this last semester. And the sum was over 257 million. And you divide by 10 the number, just to walk you through the steps. And then you're down to only 25.7 million. A small number there. You square root that, and then you're down, and I checked it, it works, $5,078 and 0.2 cents, I might add. It almost hit it exactly on the cents there. Okay, anyway, enough of that one. Take a look at the example I did in class, actually earlier today, Wednesday, Thursday, the last meetings, the live meetings before the break. Here's a standard one. The weights of oranges in a harvest are normally distributed with a mean weight of 150, standard deviation of 10. And let's ignore the 1,000 oranges for now. This is just like the example I did earlier. How many will weigh between 140 and 160? Perhaps it's clear that if you add 10 to 150, you get 160. That's known as one standard deviation. And subtracting one group of 10 gets you 140. This is then clearly within one standard deviation, and then you have the 68%. That's the rule, 68% rule. And by the way, 68% of 1,000 is 680 oranges. That's a lot of them. But now we go to what I think is obviously 2 standard deviations. And so you take the mean of 150 and you add a couple of tens. How about a 20? You get to 170. You subtract that 20 away, you get 130. That's 2 standard deviations. That's the 95% rule. Actually, we can go a little deeper than that, but we're not going to worry about it. And multiply that by 1,000, that's 950 oranges. So the vast majority of oranges is already within 2 standard deviations. If you carry it out to 3, then it's practically all of them. It would be 997 oranges out of 1,000 then. And then occasionally you get the real small orange or the really big orange that wouldn't fit the bill. I meant to do this one first because this is just about doing a z-score, but so much for that. That's not a big deal. Looking at these particular values, find the z-score, and I wish I could write on this. I'm very embarrassed about it, but I'll try to do something else later. When you take the mean of 150 and take your value, remember it's going to be the data value, 160, minus the mean of 150, which then tells you you're 10 grams above average. But then you divide by the standard deviation, and 10 divided by 10 is exactly 1.0 if you wish, and you can use the table. And they didn't ask for the percentile here. They just purely a z-score type problem. What about this one though, part B? 135 grams minus 150, we find that that's minus 15. This is 15 grams below average. And that minus 15 divided by 10 is minus 1.5 for your z-score. And you see the answers right in front of you. A weakness of these quizzes is the answers staring right at you. So I purposefully try not to look at them. But even so, it's not the best tool in the world as far as teaching this stuff, in my opinion. But they have a good collection of problems, which this generally is. They ought to hide the answers. They put them on the next page or in the back of the book so you can dig around for them. But that's just my opinion. Okay, we've seen some of these before, and all these are fairly likely to show up, except for a really difficult standard deviation problem. I do not plan to do that, of course. For a certain disease, 40% of untreated patients can be expected to improve within a week, just on their own. We observe a population of 80 untreated patients. So these people do not have any medicine. We saw a problem kind of like this before. We record the percentage who improve within a week, and that's the criteria time-wise. So according to the central limit theorem, these percentages are approximately bell-shaped, normal distribution. Find the mean and standard deviation of this distribution and round the standard deviation, etc. Well, the mean is a piece of cake. Talk about free points. If anybody misses this, I'm going to be looking very strongly at your grade. That's a huge bellwether situation. If you can't even get one that we're giving away, then there's something wrong. So yeah, leave it alone. Leave it as 40%. Don't give me 0.40% or anything like that. Just leave it as 40%. That would be fine. But the standard deviation actually involves the formula. So we use the formula. We put in the P, 40, in terms of a percentage. Do not use decimal. And then 100 minus P is 60. So as I kind of increase it, since I can't type on this. And so we get the 2400 divided by 80. And 80 was the untreated patients. That's the N as far as the formula is concerned. This is, remember, square root of P times 100 minus P divided by N. And when you put all that in, it's the square root of 30, which is very close to 5.5, 5.48 percentage points. So that's how that goes. Incidentally, while I'm thinking about it, looking at number 4, one could actually have used z-scores on this and used the table and found the percentiles and subtracted them out. That could have been done. It would have been the long way to go. Not the wrong way to go, would have been a good way to go, actually. And then one could have subtracted away the percentiles, putting them into decimal form probably, and getting the same answers. You get a little bit more detail. Instead of 68% for the first, you get 68.3% if you use the table. Maybe even use all 4 decimal places, and you get 68.26% then, which is basically saying the same thing as that empirical rule, which was the 68, 95, 99.7 rule, as we mentioned. Same thing happens over here. When z is equal to plus and minus 2, one can look at the percentiles, probably convert them to decimals, subtract them out, and you'll get 95.45%. And that's just like the 95% rule. It's rounded down to the nearest percent. Yeah, that's okay. So you can use either way. If you find the z-scores and use your percentiles and subtract them out, especially with a curve that I cannot show you right now. All I can do is show you the cursor, unfortunately. But anyway, you can do it either way. You do it the short way if you remember the, just quote the rule, and maybe it'll just be multiple choice anyway, but we'll see how it goes. Let's take a look at number 7. Use the mean and standard deviation we just got in number 6 to find the percentage of test groups of 80 untreated patients in which 50% or less improve within a week. Now, we expected 40. So what we'll have here is the value of 50 minus 40. This is the data value we're interested in, 50. But the mean, it says it right here, is 40. It's a difference of 10 points. Just call it 10. And we divide by the number we just found out about. This time they picked 2 decimal places. That's okay. And that works out to be 1.8 standard deviations. And that's fine. You can get that from the table. And when you use the table, you will see that 50% or less, which is perfect. You don't have to make an adjustment. There's no 100% involved on this one. And then you find it directly from the table as about 96.4% likely. So when we expect 40 and we're looking at 50% or less, we're grabbing that 40 because that's part of the huge territory that has the 50% or less. So that explains partly why that's such a large number. It's very likely this is going to happen. There's only a few that are above 50 that might happen that would take it away from the 100% perfection number, I guess you could say. That's still awfully close to 100% because the 50% is quite a bit larger than the expected 40% as it turns out. Okay, so here's more of a technical verbal problem. Explain the meaning of a poll that says that 55% of Americans approve of the job the president is doing with a margin of error of 3% and a confidence level of 95%. This is all this is adding and subtracting the margin of error to form a confidence interval. So you'd have to somehow lead off with the 95% of such polls. The reported approval rating of the president will be within 3 percentage points of the true approval level. Therefore, you take the 55, that was the point estimate, the one number that they picked. But then with the margin of error, you can subtract the 3% to get down to 52. You can add the 3% to get up to 58. And now we're 95% confident that the true level is in this range of values. It's not just 1 point. It's got a plausible interval of believability that we can find. So now we get to sort of the simpler ones with the small formulas found at the end of the chapter. And the poll asks 800 people their choice for mayor. And the only one we ever use is 95% confidence interval. What's the approximate margin of error? Find that M formula, or ME formula, depending how you wrote it up. And that's going to be 100 over the square root of n. N is 800. So it's 100 divided by the square root of 800, and that works out to be 100 over about 28, which leads you to a 3.5% margin of error. So you should, of course, be very confident in these types of relatively simple formulas. If you endured chapter 4, this shouldn't be any big deal, especially when you have a formula sheet. I'm just basically giving it away. But we'll use things like M or N and whatever. This is for a sample size. It uses essentially the same formula, it just looks different. It's the inverse version of it. So what sample size would be needed to give the margin of error of 2.5% with a standard confidence level? So we just flip it around and solve for N, and that one would be, we suppose you'll use the other formula, it would be 100 over M completely squared. So in terms of a percentage, you do not put it in decimal. That's probably the biggest thing to remember. Don't put it in decimal. Leave it alone. 100 over 2.5 is going to be squared. Now 100 from the formula divided by 2.5 is exactly 40. When you square 40, 40 times 40 is exactly 1600. So that's how that would be the sample size needed. A pretty large one. This would be the minimum sample size, by the way. Okay, so now we have some interesting ones. For each of the following situations, determine whether the results described appear to be statistically significant, that is a low p-value or a high level of rarity. So we're taking part A. We're walking down the street and encounter 3 people in a row with blonde hair. Now there are blondes, there are a lot of blondes out there, and finding 3 people in a row that have blonde hair, it's not very rare. It's not very common, but it's not very rare either, so that would not really be considered statistically significant. If you were in certain other countries of the world where blondes are very hard to find, that would be a different story. Now, if you look at part B, you cut a deck of playing cards 30 times. You get an ace every time. Oh boy, that is definitely statistically significant, and very much so. I actually ran the numbers on that, and that works out to be 4 times 10 to the minus 34th power. That's very, very low. There's like 33, 34 zeros after the decimal point. That's a lot rarer than 0.05. So that would be, there's something up with that. You've got a bad deck of cards that are full of aces, or you're cheating somehow that it's hard to tell. Maybe it falls out of your sleeve or something. I don't know. But there's when it's that rare and something actually happens like that, then it's undoubtedly somehow somebody is cheating and not playing fair. Kind of obvious on that one. Now here at number 12, a clinical trial for an experimental drug finds that the drug is effective with a p-value of 0.08. Explain the meaning of the p-value in this case, and would this result normally be accepted as statistically significant? So the answer is right in front of us. Maybe we'll just sort of read it. The probability that the outcome of the clinical trial would occur by chance alone if this drug had no effect is 8%. 0.08. Now, this result would not normally be accepted as statistically significant because the p-value is larger than 5%. So, effective by chance 8% of the time. That's not that rare. So maybe the drug isn't doing as good a job as we hoped it would. Now, that's headed downwards, and sometimes they use a criteria of 0.10 for 10%. And in that case, then you have a different decision. But this book is not doing that. They're going to use the 5% level. 8% just isn't rare enough. Go back to the lab, go back to the drawing board, so to speak, and come up with a better drug, because this isn't going to make it as well as it should. So that's how that goes. Now, decide whether the following variables are positively correlated, negatively correlated, or uncorrelated. Okay, this is interesting. You don't have to do any graphs. You don't have to put any scales down, anything like that. This is more of an intuitive situation. And here's a classic one that every student needs to be aware of. Your grades and the number of hours per week you study. Yes, they are positively correlated. Now, it's not to say that there aren't exceptions. There are geniuses. I've met some, a couple of them. I'm talking like 190, 200 IQ people that humble me. They humble me. And they wouldn't study that much, and yet they'd get A's. Wow, you just can't compare yourself to people like that. Perhaps you've met people like that. That's awesome. Good for them, but don't let it reflect on you, okay? Because sometimes it may not work out that way. Or occasionally, and I've been there, where you study up to 12, 14 hours a day, and I still got a bad grade. But then the guy failed practically the entire class. So me actually passing the class meant that I did pretty well compared to everybody else, but A was just about out of the question. So sometimes you get into weird situations, but mostly the moral of the story is the more you study, generally the better your grades are. Okay, let's go to part B. Positively correlated, of course. And I'd hopefully say tightly correlated. Your grades and the number of hours a week you party. Well, probably that's the flip side of part A. This would be negatively correlated. If you party 1 or 2 hours a week, or maybe on Saturday nights for a while, that's not usually a problem. But if you party every single day, 10 hours a day, then where do you have time to study? The grades would typically slip at that point. So this is where it's negatively correlated. How about part C? Your grades and the number of cookies per week you eat. Well, assuming that you don't eat like 500 cookies a week, so you can't even move, well, but that's very unlikely. So this would have to be considered to be uncorrelated. Some people do well by eating a lot of cookies. Some people do well by not ever having cookies, and vice versa. So there really is no real correlation. And even if there was, there wouldn't be much to gain from that. Okay, how about part D? The daily average temperature and sales of cell phones. Well, the thing is, when the temperature is hot, the temperature is cold, people still buy cell phones, so it doesn't really matter. That was another one that's uncorrelated. How about E? The daily average temperature and sales of overcoats. Well, here's the thing. You have to watch the direction, because you can see a correlation, but which one is it? When the temperature goes up, not many people are interested in buying overcoats unless there's like a massive sale and they're just getting ready for the cold winter ahead or something like that. But normally the overcoats would just disappear from the stores and they would go down. This would be negatively correlated, but the easier one to see would be part F, the daily average temperature and sales of shorts. So as the temperature climbs, as you get to August, September, when it gets over 100 degrees, and people mostly wear shorts. I know I do. And, nothing wrong with that. So the sales of shorts will go up higher as the temperature climbs. So this one, of course, is positively correlated. Now, I apologize once again for not having a pen to write with, but I hope that if you had a chance to look at these in advance, or of course the answers are staring right at you, it's just a matter of finding the right formula and making sure you agree with the answers. And you can always rewind me and listen again and then work it out for yourself, which I strongly recommend that you do. And I'll have a few more problems picked out for you that you can work on your own. Plus, you can just pick any others you want. Any odd problem that has an answer in the back that seems like it's halfway interesting or something we talked about, go ahead and work on them. The more you do, the better off you'll be. The more practice you have working out the standard deviation. If you've worked it out 3 or 4 times, you probably have nothing to worry about on the test. Unfortunately, I get people who really have never done it before, and then they pretend to do it on the test. And yeah, that's where work's going to matter. If I don't see your work and it doesn't make any sense, if you've copied from somebody else, for example, that sometimes, in fact, quite often, becomes very obvious to me. And then I'm quite skeptical about certain things. So anyway, show your work. Make sure you understand how to do it, not just for my class, for the future as well. So nobody will remember what you got in this class 10 years from now. But you may remember some of the stuff that might stick with you, that might actually help you in many situations. And that's my goal. I don't care if you get an A or a B or a C. I care that you understand this stuff to get by and maybe become advantageous to you in your career, and that would be amazing. I love it when people tell me how successful they were in their career later on. That just makes me very happy. So I'm hoping that many of you will tell me this in the future as you graduate and become statistically oriented, and at least don't shut the door that opens for you and then somehow make it big in your future career. At least I hope that's the case, and enjoy your career as well. It's not just having money, it's enjoying yourself as you work on something you really love to do. Okay, so that'll pretty much wind it up for today. We reviewed chapter 6.4 by looking between the cracks of the slideshow, which is only going to cover part of it. And I also tried to work through the quiz with a live lecture and the ability to use the pen. I'll be able to perhaps go back through a couple more of these during the live class that you will have on April 7 and 8, preparing for the test on either April 12 or 13, which will cover once again the second half of 4.3, 4.4, and all of chapter 6. So study hard and you'll do fine. I expect the grades will go up because test 1 is always the toughest test. Okay, well, good luck and have a nice break. If you've already had it, congratulations. If you haven't had it yet, you've got something to look forward to. So either way, we'll talk to you live pretty soon. And yes, I'm available for emails because I'll still be at home working on things. I've got another job I work on too. So, okay, that'll do it for now. Have a nice day, and we'll talk to you later. Bye-bye.